is going to be the next 2 hours is sort of like on what educational resources there are within the CSDMS system. I'll do a bit of hand waving and like trying to point people to stuff, but we also like will engage in trying the WMT, which is the web-based modeling tool that Systems has developed. Mark is the main developer of the interface of WMT, and he's here and like will be able to like help out or sort of like step in if I don't know the technical details. But I will also take this opportunity to sort of point to like the different tiers of like information that CSDMS has, and it's not just the WMT, or it's not just like serving developers and sort of the experts that we have here, but it's also bringing awareness to the public about what models are, how do we use them in the Earth surface processes, etc. I'm not going to be standing up here and talk, or I am going to be standing up here, but hopefully I'm not going to be talking here all the time, because then 2 hours becomes pretty boring. So like please feel free to like interrupt and like discuss and like ask questions. This is going to be sort of a exchange of ideas, and I have in the end like the last 15 minutes or so I definitely want to use to brainstorm with the group about ideas that are here. We need your guidance as a community, and this is my one chance, or my chance, to like solicit feedback from sort of everyone who's in the room and is interested in using these resources. So this is sort of the agenda for the next 2 hours. It looks very cramped, but it's not so bad as it looks. I will like kind of walk people through like the vision of CSDMS. This is going to be boring for some of you who've been involved for a long time, but there's always new people that aren't as familiar, and I do want to sort of embed like this idea of what is the base that we work from, or the basic ideas that we work from. I'll give you like a little demo of the web modeling tool, just so that you know what is intended with it, and point to what model labs are available so that people know where to go later on when they want to start using things in their own classrooms. I'll talk some about topical learning objectives versus modeling skills, and how both those things are important to our community and are important to our students. And that we're trying to sort of like hit both those things in the labs, and that we're trying to hit both those things in the material that we're developing. And then, so this maybe will take like 30 minutes or so, I think. Maybe a little longer if I like go into detail in the labs. But then like definitely then there will be a big chunk where we'll all sit down, and like people per table can like sort of start up, or like anyone who has their Beach accounts can like start up the WMT. We'll do like a couple of like little runs and like watch examples. We'll be doing visualizing with Panoply. I can do them live here. I have it on my laptop. But if you go to NASA Panoply through Google, you can download that software while I'm talking, and then we can like use it almost straight away. So there's downloads of this for like Macs and Windows. Like I have to admit I did not try them on a PC, of course, but it works like really easily. It easily is worked on the Mac side of things. This package is developed to like deal with netCDF files. The CSDMS team uses netCDF as their standard format for serving output out of models, whether they're time series, whether they're grids, whether they're grid stacks. So it's once you're starting to do full-on research, there may be other tools that we've advocated for before too that are more powerful than this. But if you're talking about the classroom and doing quick visualization with students, it's actually really powerful to use this package. So that's why I'm plugging for it today, because we haven't mentioned it in earlier workshops before. So like, I don't know. This was the one that I went to for a download. So CSDMS motto has been to explore the Earth's surface with community software. And a lot of that is focused on like empowering researchers and like forging new connections between domains and doing new science. Or setting up protocols so that like your models are going to be more easily shared between others, are going to be more reproducible, etc. Those are all like objectives that are there for the science community and for us to enable our community to like do more efficient modeling. But there's always been an aspect to CSDMS where we say like we also need to educate our students to be good modelers or become good modelers. And we have a sort of a tiered approach to that. Like there's a, in the basic objectives of CSDMS, there's even a notion that models are something that are getting used more and more. Like they're handed over to policymakers. They're forecasting models that come in the Earth surface processes more and more. And we want the public to be aware of the power of models and the limitations of models, and like how we are using those. And then there's a tier where are we doing an efficient job in teaching our students to like be modelers. And so there's sort of like 3 levels that we try to develop a little bit of material for in discussions in the educational and knowledge transfer working group. I think there was like always a focus on undergraduates as our sort of like main public, but we're trying to like at least like do something for other parts or like other levels and tiers there too. So as I said, like modeling is actually something that's in the core curricula of even the K6 to 12 curriculum requirements. Like it ties really into the basic process of science, and so there's an opportunity for modelers in general to like hand over simplified models or models that are fairly clear cut. To allow students to carry on little investigations, to like sort of engage in the scientific process of formulating a hypothesis and then testing your hypothesis with a model. And we do realize that is there, but it's a level of models that in our community doesn't get developed that much, except for like few exceptions. And Wei Luo, who's here, is actually maybe one of the champions, where he took his landscape evolution model and like really made it like accessible, and tries to hit that group of people or students like at a lower level, and like teach basic concept of like hydrology and landscape evolution with a simple model where you can turn knobs and test how that impacts your morphology, etc. Most of our models are not that targeted towards that. So one of the ways that we deal with that, or like that we do try to target that market, is to use the Science on the Sphere system. And I did a poster on that, and like probably some people saw that yesterday. And I put little postcards out on the table. So the Science on a Sphere are like things that are in musea. They're like huge spheres. There's projections onto these spheres, and if you have a global data set, you can project or like bring it up to the same formats that they use and like project it on these spheres. I'll like give you a quick tour on their website. So there's hundreds of spheres in the US, Europe, and Asia combined. So there is some likelihood that there is one close by in a big museum to where you are. So maybe you can take undergrads or like you can't take students. But at the same time, they do realize that they're not going to be everywhere. And so like all their data sets are also like accessible through the internet. And like the descriptions that come with the data sets that the original contributors have written are there, the materials all there. And so like you can just go to their data sets and like use those for teaching. So, like, I think we're up to 8 data sets. It takes some effort and time to like get these ready to be like projected, or get the story ready that you want to tell with your data set. Like one example that I'm going to share is like we were using WaveWatch 3. It's a global wave model, and the data sets are like basically available for everyone. And we thought like, well, that's like a good example. We'll like teach something about waves. But then you have to make a decision of what you want to teach about the waves. Like how do you make it compelling to children or citizens? And so then you have to like dissect your data set to like just focus on that specific aspect that you're trying to teach. So there's development time that goes, or that sinks into sort of developing these data sets. But to give you an example of that, waves. So some of these are not, like many of these are not ours, right? But this is one we developed. And so at the Science of a Sphere locations, people can pull these up. So if you have a Science on a Sphere system somewhere close to at your university, or like a museum close to your university, you can tell the guy or person, the instructor who's there, to pull these up. They have like a little tablet and they just like browse through them and like say like, okay, we'll do the waves, and then they'll project the waves for you. But you can also like just go in and like find through the FTP, find the original movies that go with it, or download the movies and like use them in your own classes. And so ones that are there is like, for example, this is on Hurricane Katrina, and it is like focused on the wave heights for Hurricane Katrina. And we thought it would be exciting to like sort of like teach about waves, but still focus it on like an event that's like in people's memory. And then actually the educators at NOAA said like, well, that's not in everyone's memory anymore, especially not in kids' memory. So like then we had to do Sandy as well. So so they give us advice, those kind of advices where they say like, you know, like you do have to like think about like, okay, you find a big drought in 1988 may be relevant, but like nobody remembers that drought, you know. So like it may have been the biggest, but so there's 2 people there. There's a tech, Beth Russell, that we've been really productively been working with, and they have an education expert, Hillary Petticord. What's pretty easy is if you have global maps of something. I think one person suggested to me to like drill down and find a map of all landslide occurrences that have been mapped over the world, and sort of like hand that over. Those data sets are the static data sets where it's just a map with points. They still look spectacular, but they're not as moving and interactive as a time series. But those are pretty easy to compile and like talk to them about the messages. Then suddenly the story and the message becomes the most important part. The ones that have animations or are model like sequences, they are like a little harder to like get into their formats. What the Science on the Sphere people claim is that there's 30 million people that see these. So like it's definitely like way beyond the YouTube channel of CSDMS. So if you'd want these for your classes, like the material here is written by us. There's often there's related, or there's always related slides that have like sort of the key points. There's only 3 or 4 of each per data set. And then sometimes there's lesson plans. These are targeted more like maybe the most basic undergraduate class, but they're targeted for like students and high school level. We try to like, they're linked. So like if you found one that is CSDMS, then you'll like find others that were sort of in the same batch of things. So the waves is one example. We like submitted the dams, we submitted global discharges, we submitted floods and droughts, we submitted one of what rivers do in like El Nino and La Nina years. And so that's sort of the big bulk of the last year that's been developed. Anyway, I'm not going to pull up the movies necessarily, right? So one of the things that I do when I develop these is I make an effort to share that this is a model, that they're not looking at data, that they're looking at a model with limitations. I don't go into like maybe that the numerical limitations, or I don't go deep into the limitations, but we talk about limitations. For the waves, for example, there's a note in the description that says like the buoys that were out in the water like actually recorded waves that were similar to what the model predicted. So you have like some confidence that the model was all right or was doing a good job in predicting the wave heights. And so like I try to like sort of like look at this as an opportunity to teach something about like the insights that we have about models, or that we know about models having limitations, and like pass that on with sort of the spectacularity of the movies. Okay, when we step the level up and we like move away from Science on the Sphere, then like we hit sort of the modeling labs resource of CSDMS. It's been two-tiered. There's Excel files that deal with like little exercises. Some of them are, I think Kyle said yesterday, is like, oh yeah, use your sinking deltas Excel spreadsheet with undergrads once in a while, and like it's really like something that was useful to me. So those are like super easy grabs from our website, and I think the one reason why we're not enthusiastic about them is that they're like based on Excel, and that's proprietary, and like they would have to like make them fully open source. They would have to be moved to like a Python, maybe an IPython notebook, or like something that's like a Python based. So if I go into CSDMS, so here's that sinking deltas one. So these are for instructors. Don't send your students to this link, because the answer key's there too. Yeah, I have no perfect solution for this. We can hide the answers, we can like put them upside down, but I think the students are gonna find them. But so the idea is that there's notes for instructors, like what are the topical goals of this, what are the skills that we teach in the little labs, and then there's an answer key, and there's a spreadsheet in which students do like a tiny little model step. So this one deals with like tide gauges, and like how tide gauges information over a long time is a measure of like sea level rise, and then when you like subtract global sea level rise, you might have like an idea of sinking of a delta. So there's different comparisons. There's also a bit more theory in sort of this simple like basic formula or basic model that people can play around with, and that you can like pose questions with. I often find that it's much more productive if you look at it a day before, and then like still like sort of tinker with it a bit yourself. And then like there's something unique that you have to bring to this, that is your area, or like the research that you have, and then your exercise is going to be even much more powerful, or you can put in like some slides of your own stuff and make it more powerful that way. But I think most people do that all the time already. But they should be, or we try to make them such that they're like really self-sustained, and like you could do like literally all the questions that are in there, but I think most people have more to add. Okay, then I'm going to step to WMT. So these are the labs that are tagged with something like that says like modeling with WMT, modeling with WMT. So I try to like make clear that these are the web-based models. So these require beach access. WMT just requires web-based access, but once people submit jobs, then they do need to have access to the supercomputer. So what that means for you as an instructor is that you do need to get your students to sign up for beach access, and there's like a couple days that it takes to like get that clearance that they're safe to like work on the CU system or work on the Janus system or like any system. There's a clearance. So you could not pull this off and say like, I wanted this tomorrow morning. You do need to like sort of know that it's a couple days out. But then again, I'm trying to make these labs such that they're like fairly self-sustained. They have PowerPoints associated with them, with at least sort of a base with notes. And again, like these are going to be more useful to you if you like add your own stuff in there, but at least there's a base with like the theory of the model and like maybe an example or two, or if there's papers written on that model, these will be in the references. So like just to walk you through, like what's a plume, what are the basic equations that are in there, like what has been done with this model, and so they give you a bit of guidance of what you can do with that lab. Often this is sort of the start of a lab where you use this to like have a 20-minute lecture or something like that, and then you do the lab with the students.
Quick question.
Yeah.
I'm teaching freshman design, so 80 students. Is it even possible to have 80 student pages on each?
It is possible.
Well, I can let them do like 5 people.
Yeah, like what we were doing like yesterday, for example, I knew that John Goodall would be running stuff. I knew that we were running stuff. Mark and Eric were teaching, like, and we're maybe doing some beach stuff. We did 2 things. We asked some of our really heavy users to back off for a day. So that's something that you could like email us and say like, you know I have 80 or I have 100 people. Could you put a request into people to like make it? There's plenty of like a lot of our models run on a single node, and like there's plenty of nodes. But yes, there is a bit of a possibility of like conflict or like jacking the machine. Another way I deal with it is like teams. Like if you have a team of 3 and like one person sets in the runs, but like they discuss how they set up scenarios, then like.
Is it also possible that if I ask my university HPC people to contact you, so they basically set everything in my own cost?
Yes. We've done this for like 2 clusters. I think Janus now has the stack and Yellowstone has the stack too. Maybe this is a better question for Mark.
But yeah, that would be really cool, Tom, actually. It would be beneficial for us if we could install our system software stack on other supercomputing machines. That would be awesome, actually. Yeah, let's do that.
And so it was one of the goals of this last year, I think, was to like make sure that we've done this before, and that and I think there's even commitments of several supercomputing facilities that they would be interested in doing this with Eric and Mark. So yes. And so yeah, that gets you around like having to interact for accounts as well, and then you just have to like interact with your local. They have accounts too there. Yeah. So I know like a whole bunch of people were in the CEM clinic yesterday, so they have seen WMT. I'm still gonna like tire you out with showing it a bit. How many people have not seen it? So a few, okay. So each of these like run with the WMT, and so like it has a link to the first tutorial in any of the labs that are a bit more topical. And that first tutorial just like gets you a bit of practice with WMT. Or if you go to these like labs, I think maybe the top lab gets started with WMT. That one only takes maybe 20 minutes or so, maybe a little longer, not much longer. So I'm gonna like open it up and quickly show kind of how things work. So these sign-ins are just to prevent like automatic spammers. This is not necessarily your Beach account. You can just use like I'm using a Gmail and some random password. And there's no sign-up procedure that involves us for that. So this is the WMT environment. These are like the components that are in there. And so the labs are based on like most of these components, or like many of these components. Some are like service components. Like base level, for example, is a service component. And like that is just a repository of like netcdf files. So like not all of them are gonna be models. If I want to get rid of that, I close it. So for example, that lab that I was opening was Plume, and this is kind of what the environment would look like that you would run Plume runs in. So Plume's a river plume model, so it takes like concentration of suspended load and like flow velocities, widths and depths, etc. And so typically I try to have people kind of play with things, so that they invent what they want to vary, or but I do provide guidance, and with the questions that are in the labs, there's sort of main learning points that if people published on Plume and they were excited about the Coriolis effects and like built that into the Plume, and this is your tool to teach about Coriolis, then there's usually like we try to hit those aspects of models. What people also learn are like little skills. Like they'll be able to like work with these netcdf files. You can make them aware that if they tick on these like output files, they have like these odd names, like very odd long names. So model, grain class, 0, deposition rate. Well, these are like standard names, and standard names are a feature that allow variables to be passed around between different models. So for example, model grain size class 0 is actually the stack of all the grain size classes. And then deposition rate is like the meters per day that Plume would deposit in a certain cell. And so I'm asking that output file, but at the same time, this would be something like setflux could understand this as well. Or if it's an input parameter and it's like river discharge at river mouth, suspended load class 0, then that would be shared between the BMI of hydrotrend and like the input that setflux takes. So it's one of these places where not everything about the model is disclosed to the students, right? They're not seeing the real code here, but it is with these things that you can see that, you know, there's a structure behind this and there's protocols behind this, and that it allows coupling between different models, etc. Often the labs have in the public domain, over here, public, oh, wait, I didn't do that right, sorry. So I tick that public label now. So like all the public runs are available as well as my own runs. And then there's one that says like Plume EKT Lab Simulation 1. And so if you don't want to have students mess around with anything, or it's like really a quick and like you only have 20 minutes or something like that, then like these examples are like already wired up and they have default parameters that are the right settings. And so you can open them up. And then, so these parameters are sort of given that they'll be like a successful run and not out of whack. Or one common thing that often happens is that people write these huge output files. In this case, that's very hard, but when you run longer simulations and you have like output at every time step, that usually results in very large files. So that's something to watch. If you, like Tom Su was asking that question about if I have 80 students and they all like whack the system with, right, with runs that have a grid and it like gets written at every time step for like 30,000 time steps, like that's gonna bug things down. So so be aware of that. Like we try to control some of that by like giving useful defaults so that people don't make that mistake all the time. But that's one of the common things that happens. Yeah, I think here we just have this. Do we have other parameters there still? Anyway, so if I'm satisfied with my run or with my settings, then I can run over here or save the run first, and then run. And so this is the moment you like have to submit your actual job script. And that's another time where like if you're teaching what this is all about, you can tell your students and make them aware that like, yes, they're actually submitting a job script or a text file that generates a job script. And they're running it on a different computer and not on their own computer. And then to see the status of a certain run, there's this reporting window. And so like, this is a very fast model and it's one time step, or like it's a steady state model. So like, it's already done. And you can download here to your own machine, which is for classes probably pretty easy. In huge computer labs at universities, like it's not always easy to like get FTPs and SSH connections up, like because there's firewalls, etc. If you're familiar with that and you're like have dealt with that before, it's resolvable, or sometimes it's just a matter of like talking to the IT person of your classroom. But I think this is fairly powerful, like instead to like just download these like zipped up directories to your own machine. What these will contain is the model output, a log file, the original input files, the text files that the model was driven with, as well as the output that you requested. So let me open this one up. Wait. So this is what that text file that used to drive this model looked like. And basically this whole WMT filled in the new values into the text file that has been passed into Plume. So you can still go back and like save these by run and like still go back to the original parameters that you put in there. Are there questions so far? I don't know what that is. Okay. So how much have we used this? Well, the WMT, I mean the CMT has been, I taught with a couple of years, but then WMT has now been used in sort of 4 intensive, like longer clinics with like a 4-day school being the longest one, where we did like sort of a source to sink sequence. Some of these clinics are more like an hour, like here, or at NSET it's about a day. So like they're variable of what, like how many pieces you can link together, or whether you just show off one little model and like grab one of the less complex models. We try to keep a good integration between information and this WMT. The metadata that we collect for models is linked. There's links from WMT to the metadata. There's links to model help pages that we maintain. Like usually we've written them first and then like asked the developer to like add or improve them. So it's not as if you just go in there and start running a model. Like there is documentation associated with things, and you can go grab it. So the way you get there is like through these like get information, and then there's like help, model help pages associated with. These are maintained on our wiki. Oh, so they're on a wiki, so anyone who sees that we made mistakes can change them. We're not like so active a community that we're like regularly changing all these documentations, but they're there, and people, if people have like changes, they're basically up to you to submit. Okay. I think I went through these, most of these. Okay. Who has a beach account? Plenty of people. Mark can maybe join that table if there's no beach account there. And then, was the table in the back is a beach account there too, right? Yeah, okay. So we can do the hands-on table by table. I think there's the coolest lab to do is maybe the CEM lab, but like some people did participate in the CEM lab yesterday. So another suggestion would be the Hydrotrend one, since Mark knows that one well too. And so I think people in the back, do you guys want to do a run in the CEM lab? Okay. Who would like to do like Hydrotrend instead? Maybe everyone wants to rather do CEM. That's fine. It's quite spectacular. Okay, so let me like pull that up. So go to this website, https csdms.colorado.edu/WMT. Peter.
Can I just ask a general question?
Yes.
Related to what you were saying.
Yes.
Right from the beginning, this has been an amazing research tool. I was completely on board with the componentized vision. What concerns me a little bit about this as a teaching facilities is two things. One is the complexity.
Yeah.
Even as if you go through that list of parameters, I think there's enough in there that many students, their heads will just explode. Looking at that list of parameters, that's one issue. Maybe that's, you can deal with that various ways. The other thing that concerns me, I suppose, is if this is really successful, people begin to use it day by day in teaching, one could envisage a situation where you have days where you've got, say, 10 classes
I think there's sort of different questions to that, or like answers to that. Once we get hundreds of students at the same time, like running this, maybe then, I mean, yes, you have to like sort of have a vision that that may be the case. But then there's Janus. Janus is like way more big than Beach is, so like we could easily accommodate a bunch of classes there. So, and Janus is really close to like our expertise. So that's one way to go, to like sort of like make it distributed over different platforms, or what Tom was suggesting, he'll just bring it to the supercomputer at his own institution, or, you know, like do it that way. But then the other way is just like freezing it in time. And then the only thing you lose basically is that if a person has like made improvements and we had frozen it, then like these are going to be on Beach, those are going to be reflected if we import them. But they wouldn't be in their teaching frozen version. But yeah, there's definitely an option for that. Yeah, Mark, please speak to that.
John Goodall really wants us to put this on like Amazon Web Services. We have our cloud as well.
Okay. So sorry, just to translate that for me, does that mean it will become more distributed onto many different computers?
Right, you can just log in from anywhere. So it would be a service in the cloud.
Okay. And where the jobs might be reached, just where. Yeah. Okay. So I think that probably then solves it.
Yeah. So that's an idea for future work. John Goodall is pushing us in this direction. So it hasn't been done yet. We haven't figured it out yet, but it's an idea.
And so the other point you brought up is like, how complex are these models, and can students like deal with sort of like all these parameters that are there? And I think the way I deal with that is to like use the labs as their guidance. So do I still have them up? No. And so in this case, I only ask them to like change so here's where they start like changing things, like 2 parameters. And they're sort of like really, I think they're fairly intuitive ones, you know, like just temperature and precipitation. And like, how does that affect discharge? But then these are sort of, I think in my experience, they take about 3 hours or so. So you have time to like introduce them to what kind of parameters this model has, what are the underlying equations, and thus they can make a hypothesis about like, if I change precipitation, should I get higher discharge or not? So we're trying to like make it easy for people to teach with them and like just focus on a few parameters. None of the components have like all the flexibility that they have when they're a code in the WMT, but we're trying to make at least like as much flexibility available to people, and so that if a person is a bit more serious and they do want to do a run, or like they do, like in the classes that I have longer time, I have a final project, and then I want them to tap into like as much resource the model offers, if they want to do like their own basin, or they want to do like a case that is out of the realm that I've done, or
what level students are these?
these were they're usually grad students, so masters and PhD both, and they usually do it in like the time that they still take classes, so they're not like, you know, like completely savvy about everything already, and like, for example, in NSET, like the ones, well, that's basically always been true. There's always like some that are modelers and they have like sort of an edge to the others. But definitely the people who are field people, they have exposure with this. And if I survey them afterwards and ask them for like, did they learn anything? Like, what did they learn? Like, one of the things I think that I find a great success is that if I ask them, do you now feel more familiarity with like submitting jobs to a supercomputer? And they all say like, yes, I'm like so much more confident that I could do that. Or so like, I mean, that seems like a small but good step. Yeah. So yes, I tie down the complexity basically by having followed the labs and like not have people tinker around with too many parameters beyond beyond the ones that I think are really dominant in a model. And usually with if you do it as a sequence, like for example in Nanjing University, we're teaching 4 full days, and there was like a bunch of us more lecturing on like models and the theory, etc. But we would have labs every afternoon, and then the last afternoon there was a bit more free form and people could do something, and then always people come up with much more ambitious ideas. I think Mariella was one of those students too, where she was like, I would really like to do these fans in Venezuela that I know well and that are like a huge disaster there. And like I was like, I'm not sure we have any model that could do that really soundly or something, you know, like, so that there's a process of sort of saying like, these are your options. You can only do such and such problem or look at this model for that problem. But like most of the time people dream up like much more complex things than the models can do. This may be Courtney's experience in the Brahms labs too. Cool. So are people in here in this window? Do I see, can I get hands up for like, does every table have one? Okay. So how about we load this like CEM waves and avulsion example. So like if you do open model here and you load this open CEM plus wave plus avulsion. What's up, Mark? Yeah, are people in? They found this example? So what you are looking at here is a coupled model configuration where CEM, the coastline evolution model that Brett Murray and Andrew Ashton have developed, is the driver. So it controls the calls to the other components. It controls the time stepping. But it needs certain things. For example, CEM was designed to do long-short transport, and wave has been expanded to do wave-dominated deltas. So it needs waves. So you have this component waves here that has to be like wired up to it, and that's what this example configuration has done for you already. So here's waves, and if you click on this little arrow here or down arrow, you'd get the parameters of waves. And so if you're most interested in teaching how higher waves or different waves influence a coastline, then you would want to play with the wave parameters in this and like change wave heights, or these are like really 2 dominant factors in this particular case. I'm not going to go into the details and the theory of how long-short transport and asymmetry in waves, etc. That was like, you got your chance yesterday to like learn from Andrew, who's the expert on this. But for the sake of doing a run, we are going to do a run and like use some of these. So the waves at 1 meter are like a good setting. These asymmetries are pretty extreme. So like we're expecting a pretty extreme output in the sense that waves come in under a high angle here, and there's quite a bit of high waves. So then another part that this model takes is it takes a river flux in. So that's under here. And again, this like standard configuration has a pretty high river flux. So like we're expecting to see a wave-dominated delta, not just a longshore transport coast. You can like make that smaller and you'll like get closer to a more like a longshore transport system. Or you can make it big. I think this is pretty big for this domain. So like maybe keep it like maybe we can do 200. And then I want to make sure that my time step is not like so long that it takes us forever. So since CEM is the driver, I went to CEM for the time step. We have 12,000. I think it took us about like 8 minutes or so to get through 12,000 time steps yesterday. So like that sounds pretty good to me. And I'm saving out these 2 netcdf files so that there's output. And it comes every 500 time steps. So let me submit this run. Okay, it's running. I hope. So Eric set this up so that it once it starts like ticking through time, it does respond to this page. So you can like keep a little bit track by refreshing like how far you are in your time that you set up. I find that useful because if you don't know like how long something's gonna take, it's kind of frustrating to like either it's gonna be 15 minutes or 2 or whatever. So this will chuck a bit. We're only at 700 time steps now. Okay, it looks like there's a bunch of runs running. Good. We can take this time that things are running to like discuss, or like if people have questions or suggestions to make this different or better, then we'll gladly hear them. I think I still have like something in response to Peter Burgess's comment. Basically, if there's a need for models that only have 3 parameters or 4 parameters, it is a matter of just changing that interface here. And like we can like hide as many as we want. It's just that we haven't done it. But if like there's enough consensus in sort of like the people that teach with this to say like, we just want to disclose precip and temperature for hydrogen, we just want to disclose Coriolis for plume, and that's it, and nothing else of the whistles and bells that are under there is available to the students to change, then that is actually a fairly easy thing to do.
I suppose if you're at the point where you're teaching a class of like 80 undergraduate students, then maybe you've got an argument to do that than if you've got 10
Right.
students.
Right.
Because 80 undergraduates, if one or two of them change something without realizing, run the model, and then time that you may spend explaining to them what they've done wrong and so on.
Right.
I think that would be my, I guess, that's what I would anticipate would be the reason why you might want to do that. I think you're right, see what happens.
Right. Yeah, you're thinking sort of like the future vision of this, and like, can you upskill the whole system?
As we discussed yesterday, we as a community want to be teaching more and more graduates to be modelers, or at the very least model users. So I think this is going to be increasingly significant in the world. So yeah, I'm just trying to anticipate if I did it back in Broadway, what would the issues be? And I think that might be
One of them.
one issue.
Right.
But it's like with a big classroom, like I'm trying to help all the
Yeah, no.
you don't want to do that more than you have to, really. You don't have more problems to deal with than you.
Right. I think what that boils down to is also like, is it just model use and like running a model, or is it more like, do we want them to be modelers and like be savvy with like going into the computer and like, you know, like changing something on the, like they could see their jobs on Beach if they're if they know how to SSH in and like check the job list, etc. And so like, I think increasingly, yes, you want that. If you want grad students to like model with you and you want them to use ROMs, then, you know, like you want them to like learn those skills too. And so this could be a vehicle where you get them started like that and like sort of wean them into it. But if you have 80 undergrads, then that is not the goal.
Well, I mean, I think ultimately it would be, so you would hope that, you know, a certain percentage of those
Right.
go on to the
Right.
stage
Yeah.
that you just described.
Right.
Whilst there's that many, and whilst many of them are not even necessarily going to stay in geoscience, they're going to go and do other things.
Right.
The focus is on running the class efficiently so that they get their learning outcomes, and you don't spend all your time with one student trying to figure out why.
Their VPN wasn't working. Right. Yeah. I'm going to quickly download like a run from yesterday and sort of show you how to visualize this in Panoply, so that you have an idea of like what we'll do with the, or that people can like follow along once their simulation is complete. Low bed load. So if I have that download here and I unpack it, I would go in and like, since I'm most interested in the coastal evolution aspect of this first, I would use this component and find its output file. And then once you've installed Panoply, it will like automatically recognize this as an NC file. And so you can just create plots pretty easily. So what we're looking at here is like the top is sands or like a sandy coast. This is a ramp ocean. We're looking at like the ratio between seawater to sediment depth ratio to like sort of like really clearly display like where the interface is between the coast and the or between the land and the ocean. And so for this run, we did 6,000 time steps, I guess, if I did the 500 interval. So I'll just run through it like this. And so this is like what the river sediment coming in and the waves working onto it, and how the coast evolves over the different time steps, or over the different 500 time step intervals. If you just use this kind of software, you cannot do much analysis. So you can basically look and compare, or like formulate a hypothesis of what you're thinking that would happen, and then like look at what happens in the movie. That's kind of like one step of like looking at data and like analyzing data. I think if there's one disadvantage of like going to these like packages, is that it's not, you need something else again to like really analyze data, like how much change was there? Like what is the mean if I have a time series? What was the max if I have a time series? And so there's several suggestions in the labs to like go to either other open source software, or like in MATLAB or in Excel, just do basic calculations with the data that you've created. And often when it's time series, I find that more useful than just looking at it. One open source package that we've been like looking at lately that Mariella suggested is this. It's called Plotly, and it's really easy to get time series in there. It's not as good with netcdf file, but many of our models also have a native format, and those are often text files. So, so if you want to keep everything in open source, or you teach somewhere where you're not confident that people have Excel, for example. The University of Minnesota did not have Excel anymore, or any Microsoft. So that actually caught me off guard. I had not expected that. So for basic analysis, you still need to go to some other package. But for these map views, like I think these are like really powerful to make little animations like this. Are there any runs completed for people already? So, much silence, maybe not. Oh yeah. Stephanie's table, did you guys change something beyond what I changed?
I don't think so.
Okay. Does it look good? Did you grab it already? Okay. I'll grab your guys' one and like show people. So it looks like this one starts out with 2 rivers, or maybe even 3. Well, it's actually quite cool. Tom?
The river
ROM, like we're 90% there with like having the ROMs community dubbed it ROMs Lite, but like a version of ROMs compiled that can run like little river plumes, has like a sort of a shallow bathymetry, multiple river mouths is possible too. Courtney can probably highlight a little bit more too. We've been working on it together, but like we didn't quite complete it. This plume model is it's just an Albertson plume equations, and so it's a steady state plume model. You could not do like a sort of a varying, I mean, you could do varying extents, but it just solves it for like a meters a day kind of extension. Yeah, so like it does not nearly have as much capability as the ROMs plume would have. Do you want to?
Well, yeah, I mean, the ROMs plume model that we're working to put on here is an idealized version of ROMs based on the river plume 2 test case, if you're familiar with that. So it has one river coming out onto a pretty uniform continental shelf with a long shelf current coursing it. And I think it wouldn't be easy to add another river.
Right. Okay.
That might not be hard to change the discharge of the river or the stream that be a long shelf current. When we have sediment coming into the river and wave resuspension, you could change the sediment concentration pretty easily, probably the wave energy.
Yeah.
So that would be good.
Yes.
I'm not teaching.
Right.
Actually, I think now I'm thinking this is definitely not for freshmen, but really it's good for senior technical elective, senior undergrad.
Right.
I think graduate students is definitely great, but my personal feeling is that it's too late. I think for graduate, if you want to get more people interested in modeling, I think we have to do it early.
Uh-huh.
And I think at least in our university, I think our junior, senior graduate, undergraduate students should get more exposure to these kind of things. To get them interested so that they will have some experience with this kind of thing and realize, oh, it's not that hard.
Right.
To model.
But so the I think the cooler thing of like using ROMs Lite compared to this plume is that yes, you suddenly introduce waves and like sort of the ocean climate, whereas the plume here is like a totally river dominated plume, and the only thing you can do to like have currents is like divert the axis of it with like a constant current. And so like when we were looking at the River 1 plume case, or I forgot what the exact name of it was, I thought that was like really the added value, that you see this interaction between the two domains where, and then the other thing is like it does the bottom sediment transport, which this plume is just rain out suspension to the bottom of the ocean, and it works with like saddle rates that are empirically tuned, whereas in the ROMs case, like you'll have a whole added dimension of currents and waves, much more process based.
I haven't taught 80 students, but I mean, one intermediate step to having them run the model would be to analyze model output. So you could show them how you run the model and how you set it up, and then give them problems where they analyze the output. Short of having them.
No, but I think the idea is to get the heads. It's actually no, because if it's more of a senior level courses, it's not going to be.
Yeah.
It's going to be. It's actually much easier.
I usually like to give the students something that works, like a run that works, and then I've only taught to graduate level students, and then have them change the model somehow in the run. And they come up with all kind of ways that they like to change the model. And usually I'll give them a list of, these would be easy changes to make. It's easy to change the river discharge, cubic meters per second. It's not easy to change the number of rivers or something, you know. And some students pick the hard things, some pick the easy things.
So one disadvantage, if you don't know these models, then like you have to invest a little bit of time to like sort of figure out like how they work, or like if you give the students full freedom to like touch all the knobs, then you're going to encounter knobs that you hadn't thought of. So anyway.
It's not a bad learning outcome to realise that we don't know all the answers.
I did know that already. Yeah. This is a coupled run, right? So we have an opportunity to play not just with wave climate, which is what we did before. Is that doing anything? So this like building of like hooks and I don't know, like how to describe the sort of the wave dominated features in the, so this would be the whole wave dominated delta, and then these are the flying spits was what we were talking about yesterday, or sort of the undulations that the longshore current causes because of the waves breaking under an angle. In this case, we're running this with, I think, 2 rivers or 2 distributary channels. That was something that CEM before didn't have, and so like there are opportunities by the fact that this is a coupled model, so that you can start thinking about different domains, or not just longshore transport anymore, but like how does a river interact with longshore transport. That this whole exercise allows you to explore. And so the way you would do that is you go back to this web modeling tool and you start like looking in what are the parameters in the components that have more to do with the land or with the delta. And so in a Volgen, for example, oh, here's another question that often comes up, and it's almost as if it's a design question that we don't have the perfect answer for. But if you have a grid set up by the driver, then the other components like may have settings for a grid that are irrelevant for that run. The driver controls the settings for the grid, the driver controls the time stepping. So for example, in my default here, like in a Volgen, for whatever reason, like maybe we should clean this up, but for whatever reason, the time duration is 36,000. That does not have meaning, and it does not get read, because CEM is the driver of this run, and so like if you go into CEM and you see what the clock is there, that is what your clock is. And I think Mark and I have talked about graying out things or something, but we haven't solved it. And the easiest thing would be to like clean them all like up very, very nicely and make the defaults at least the same. But as soon as you like change it, then students are going to ask you, it's like, oh, do I also need to change it in the sort of the components that get drawn into? And then the answer is no, they don't need to. The driver controls that. So we have a, in this particular run, or the defaults that were here, or like in the example, is maybe different from yours. I'm not sure which example I pulled up and you pulled up. But you can change something in the delta plane geometry and the distributor channels here. And that's in these angles. The way this works, I don't have a blackboard here, but you have an incoming river, and then you have like a sort of a deltaic shape, and there the channels move around. If it's one channel, it will just sweep around like this, and like it has a random sweep. The angle of that random sweep is controlled over there. And so here, this is a very narrow angle, so you'll have something that's like pretty much locked in place, and like there's only like super tiny fluctuations that are possible. That means, if you will ask your students to cast a hypothesis, that you have like faster progradation, because it's doesn't get spread out over like a whole stretch of coastal zone. The sediment doesn't. It like gets always like fed into the same position. There is a feedback between these components, and like one of the feedback or places where feedback happens is here. It's in the exponent we use to divide sediment over different channels in the delta. So if you have different distributary channels, you have an incoming flux, how do you decide like how much sediment goes into one and the other channel? And that goes by length. The longest channel, the shortest channel gets the most sediment. If you jack up this exponent or change this exponent, it will like make it more unequal. The feedback that's happening is like while CEM is evolving the coastline, you're like getting a larger and larger delta, and thus you get a larger and larger long channel, and that like asymmetry between the two distributaries becomes bigger and bigger. So that is one of the places where like CEM could not have done that on its own without this avulsion component. The avulsion component would normally not have a feedback of where the coastline is. So like that was sort of a new aspect that was introduced in this coupling of or this particular coupling. And I was excited about that too, because it sort of teaches you that there is a use in combining components, you know, like it's not, I'm just passing information from one to another. There's actually a process control between the different components. It's maybe more for the advanced student. So what if we change this like river angle to a like really wide angle? It's gonna look like less spectacular maybe, or more broad crested, I guess. And this will be even more pronounced if I would have like 3 rivers here. So let's do that. I'm going to make it a little shorter, otherwise we wait so long. Do people have success with like grabbing their own package of the tar file and visualizing it? I see some nodding. Yeah, great. Okay, you're all set up to use it in class then, basically.
Hey, Irina?
Yes.
In Panoply, did you see a way to automatically do like an animation other than just manually?
There is. Yeah. Yeah.
Don't worry about it. I'll figure it out.
There is, and it's also like super easy to export your animation. So like it's kind of cool to like generate quick results and then use them for students. Way?
Before you move on, I have 2 questions.
Yes.
So first of all, this model, is it possible to, for the users, load their own data on the model?
In this particular like configuration that we are doing, no. But there's other models where that is applicable, and then the answer is yes. So yes in some cases, yet no in other cases. I'll show you a quick example of how that would work.
The other question is, if I have other model I like this interface.
Yeah.
How do we do that?
So then you have to go through this endeavor of like making a BMI, a basic model interface for your model. Eric and Mark support, like help people out with like doing that. But like we're trying to get people to sort of like say like, these are the parameters that my model passes on or like generates. The BMI discloses the model resolution, time stepping. Like there's sort of like a list of like standard things, and you have to like put that above your own code to make it available. The language, I'm not sure if you would want to do this for Wilsim. If I'm like, I don't know that. But what's that written in? In which language? In Java. Okay, so that's compatible with with this framework. So the languages that can be done with is C, C++, like all the Fortrans, I think, Java, and Python. So any model in those languages, it doesn't require a huge investment of the developer to get it into this framework. So it would definitely be an option, and you'd be very, very much welcome to like do it. And this year, Eric pushed to sort of make that whole process easier, and they taught this clinic yesterday on how far that is now and where people are now. But like even in the next half year or in the next year, that will still be a little bit more easy, I think, or that's the goal. But usually we just sit down with people a bit and get it done like that. So to show you an example of a model that does take so here the model needs a file that is like particular to a particular basin, and like so the standard runs were like inspired on the Waipoa because there was like that was what the model was doing at the time, and so like we have that as a sort of a base case. And if I give this to students, I'd always tell them like this is the Waipoa basin and like give them some information about that basin. But you can also like say like, okay, well, I'm not interested in the Waipoa per se, but I want to do the eel because that's one of those like sort of famous hypsometries or like famous basins where people worked on. Or so you can choose from some of the examples, or you can read up on the documentation of what kind of file this is and then load up your own file. So here you would have a file that you would then supply, and then the model would run with that file. And so there you get much more risky because if the header is wrong or like, you know, it's research code, like it's not that protected. So you do need to get the files cleaned up to the format, but it's possible, yeah. And actually for this particular example, we're working on a structure to like grab that from geospatial data sets, like from GTOPO 30 or SRTM data. Stephanie Higgins wrote this like module together with David Torbotten to like delineate drainage basins. And so like basically what she's striving to get to work is you drop a point anywhere in the world in a river, it delineates the basin with that and like lifts out the hypsometric file that's needed for this model, so that there's a much more geospatial aspect to that. And she, like it's all working in Python on her machines, and she like got rid of like any non-open source dependencies, but it's not in WMT yet. So that's something that's going to happen pretty soon. Are there any other questions still? You're getting bored with the looking at CEM results. Oh, somebody did a hydrotrend run. When I taught in a petroleum geology department, there often the students get a core and they have to guess the environment. So like you can do tricks like that too, where like you give them the output and you like ask them to guess for the parameters that build that core. Like it's possible in setflux, for example. And we used to have like quite a bit of fun with trying to guess it. And basically people would do like something like 10 or 20 simulations to figure out whether their guess was right based on the core, and like often they would not get it. I think I already grabbed that. So this was the one with the 3 rivers and with like a 45-degree angle. And so you can like distinctly see that there's like different sources of sediment along the coast, and like the waves beat down like two prograding deltas basically. So apparently 2 of them are close and 1 is further out. So this should be hydrogen output, I think. This is one of the examples. I'm quickly going to point this out because you'll encounter this. But if models had like their own format of output, often it's preserved in the structure of the WMT. So like, for example, Hydrotrend had the capability of writing ASCII files. Well, they'll still be here too. So like the NetCDF is the standard that we're trying to get people used to and get people familiar with. But if these were like useful files to people, they're still going to be there. You just have to like sort of look in the directory structure and find them. And so for analysis, I often still use these instead. But you can also look at the NetCDF file of discharge, for example, which is this one. So this would be a time series of, I forgot how long that Waipoa run is, like maybe 10 years or something. Anyway, you see like the peakedness of the precipitation events. This is a basin in New Zealand. It's very moist, and the river responds quite flashy to it. I'm not going to show you how to clean up these plots and like really make them nice. I mean, it's just a matter of like browsing around some in Panoply. Good. I have some words on like future developments that are really near. And I'd like to then open it up for the last 10 minutes or so to sort of like brainstorm about ideas. And like already there were like a couple of things that popped up. And maybe Sam wants to pitch in some then too. Sure. Yep. Because I think many of you were not at the Dakota clinic that Mark taught. So we have a first beta version of Dakota, which is a package for model assessment. And so this steps it up to like a little higher level, and like maybe not the undergrad class that we were just talking about, but definitely like these are skills that you want to build in like students who are going to seriously model, like to like be able to do sensitivity testing and to do model assessment. Dakota is developed at Sandia Labs, and we're just providing a binder to Dakota, and like basically our models get wrapped with these methods that Dakota offers. And it's an alpha version, I got told, but I am going to show you a little bit of how that would work. So for now, this is built as a proof of concept, and it's like wrapped around Hydrotrend. So what you can do is, instead of doing one run with like certain default settings and like one setting that you change, you can start setting ranges for parameters and then look at output in the sense of like multiple outputs plotted along a line against those parameters that you changed. So there's like 3 methods that have been built in for now: the centered parameter, multi-dim parameter, and vector parameter. And Mark made a nice slide to show what that looks like, that I'm going to pull up. They look like this. So basically, these are the 3 configurations of how you would like run those ranges. Like either you have it as a vector, or you go from one point and like go into two directions, or you do it as a sort of like a grid in a space of like parameter 1, parameter 2. And so like somebody commented in the Dakota clinic and said like, well, we would normally script this, right? And that's entirely true. It's like a totally valid comment. But I think the power for teaching in this is that people get used to the idea that like, oh, you know, like I can like do this systematically. I don't have to like sort of like sit down and intuitively start like making things really large or really small. I could step through this systematically. And so that's the idea of like WMT and like teaching some of these like sensitivity testing methods. And so we looked a little bit at that hydrotrend example, not in detail at all, but this is a basin model, and it predicts sediment loads and water discharges based on like a suite of parameters, but like ones that are picked here are sort of like dominant ones. And so you can like see a list of like parameters that you can systematically explore, and then output gets written into these files, but like the parameters that you want to explore the sensitivity to these, you like write into these. So like, for example, if you're mainly interested in how the water varies with the precipitation, you like would click precipitation here and then test it against, or like look at the sensitivity against the water discharge. And then so like here you then set like what your values are. Like for example, the Waiapoa gets like 1.3 meters of rain. I'm making this up. But you would go from like 2 meters to, or like from 1 meter to 2 meters, or, and then you can do that in so many steps as you specify. And then automatically when you submit your run, like hydrotrend will be called like the number of times that you ask it to. And so instead of a one value as an output, you will have like a sensitivity to certain parameters. Do you want to comment on like how many models we want to wrap this around?
Sure. So this is definitely alpha level software. Probably play with it and find that out very quickly. But the goal is to get this wrapped with all of the models that are currently in WMT. And also, as Irina pointed out, there's only 3 Dakota analysis methods that are currently available in this interface. And that's purely because I got 3 finished in the time before the meeting. I was still doing this like last week. So Dakota has a broad library of analysis. I've just done a couple of them. There are a couple really simple ones, but there's so much more we can do. And now that I've got the simple ones done, it's actually pretty easy to start doing more difficult ones as well. So that's the goal, to add more analysis as well.
Right. And so mostly this is going to be a resource for researchers. But I think I'm definitely going to put up like a few labs that like tap into this as a method, because I think it's one of those other learning things that you need to learn as a modeler, that like one output is not going to be like the one that you get published. You know, there needs to be error bars around your outcomes, and like people need to think about uncertainty, and like this sort of provides a nice like first level exploration of model sensitivity for now. But there's model uncertainty is among the Dakota methods as well. So we're striving to like get that into the curriculum for students as well. Tom?
Just a quick clarification. So in the hydrotrend, each case is using one processor, right? So when you do Dakota, you're doing like 10 different realizations, and you're actually using 10 processors.
I could do that, but I am not. I'm just using one processor. But Dakota has actually a couple levels of parallelism built in as well. So that's another thing I need to figure out, is how to implement those parallel
you were teaching at the same time.
Yes.
So,
Right. So, because I'm thinking about a more complicated simulation like models in the future, and each simulation may take 200 processors. Right. And so, if I actually want to do that, something like that, I have to do 10 simulations, so it's 2,000 processors. Right. But I think that's great because if you write a XC proposal, that's what they want. They want you to learn their processing. And if the goal is to have better possibility analysis.
And also one small side comment as well. These techniques that have been are crude, there are also more advanced techniques where you can basically get approximately the same results, the same quality of results, with fewer iterations as well.
so do people see a use of this if they would teach like an advanced class? I see like a couple little nods. Okay. Yeah. I mean, honestly, I actually think that it is quite a valuable little experience if people would do this with Hydrotrend or like some of the simple standalone models to sort of see like, oh, you could do this systematically, and then I'm suddenly looking at a surface, a response surface, and that's much more useful than like me sitting there and like basically creating my response surface over time. So it's good to sort of like know that capability is there. So in that sense, I do think that there's a market even in the sort of like the lower level. Good. What else? Future. So like basically, this was one of the results of the runs that Mark was doing, where like he varied like 2 parameters and then looks at the surface that is like the response of like, I think this is discharge versus like temperature and precipitation. Hydrotrend runs really quick, so like that's pretty doable for like hundreds of runs. Even in a class, it's totally doable. And then the other thing that I should add is Mark's pioneering these IPython notebooks to go with like labs. And so I'm a great fan, but I'm not very good with them yet. But the idea is that you like, when you do your analysis of your output, you would like keep track in your IPython notebook of what you're doing in steps. And it's almost as if you make the programming of like an analysis of your output much more accessible to your students, and you could share the notebooks fairly easy. So yes, they're a powerful tool, but they're not in place for all the labs yet. But that's something into the future as well. And I think the last thing that I wanted, we talked about Rom's light. Maybe this pre and post model assessment or like assessments of the clinics is something that you would want to comment on, Sam? Of the labs, yeah.
Okay, so who here, raise your hand if you do or are planning to use any of these tools in a class. 1, 2, all right. Would you do me a favor? Oh, and who here would be willing to, if we had an assessment template, so so you write, you have the students, the night beforehand, they fill out a one-page form, just like your class evaluation form that you do for your courses every year. We'd like to do a pre and a post evaluation to sort of document the success or failure of the learning objectives. Would anybody here be willing to incorporate that as well? Yeah. 1 person? 2, 3, 4? Okay, good. Would you, if you are, would you send a quick note to me and Irina with just like systems EKT assessment on the subject line, so that we can get you in? And what we want to do is for a whole series of these tools, of these educational packages, we want to begin documenting, because those and then incorporating first of all, so we can improve what we're doing. And also, this is part sort of documenting and showing how we can improve our model use training as part of a long-term strategic plan for systems in general, and for the EKT, Education and Knowledge Transfer Group in particular. So, and this not only applies to WMT, but we're also interested in some standalone versions like ROMS Lite, like simpler analytical formulations that might be in an Excel or a spreadsheet, or God forbid that we should use something that's not open source. Maybe we could use a Google Docs worksheet or something like that. But so, and the ultimate goal for this, some of you have already heard this, is to put the information together in an educational journal article, and those who participate will get authorship. So it's a little carrot that we sort of toss your way.
Very little carrot.
Yes. It may be like one of the lunar orbiter articles. It's got like 30 authors on it or something like that. But it'll still be bona fide. And so anyway, anybody who's interested, just send a quick note to the two of us. And my email is sjb@lsu.edu. And I'm also listed on the systems wiki as the chair of the EKT group. sjb@lsu.edu.
So what is the timeline?
Well, what we'd really like to do is, this is probably because we're going to be rolling out like introductory undergraduate, sort of introductory graduate, and then maybe some more sophisticated graduate models over the next year. So what we'd really like to know, if people are going to be teaching courses fall semester or spring semester, and they'd be willing to use something like, well, I'd be willing to use an undergraduate Excel package, or a standalone numerical formulation, or a small course with a WMT. So what would be your preferences? But what we'll do is we'll get back to you guys. We'll come up with a checklist of who's going to be interested in what, and then over the summer we'll come up with a template for evaluation. And we ideally would like to have these things all parallel, so we can compare apples to apples for each one. Where do things work? Where do things not work? What's successful? What's not successful? And so on and so forth.
I said this to you yesterday,
yes.
but I also think that as part of the assessment, you should ask the instructors
Right.
if they felt that their lesson objectives were met.
That's right.
And not just rely on the students.
Yeah, and of course,
I've done some really cool computing labs with first-year graduate students, and I thought they went really well. And then the students complained because they had to use a computer or something, something that I thought that was kind of like the whole point, was to get some people who weren't used to doing much on a computer to go on a computer.
That's
so
right.
The evaluations from the students were really negative.
Right.
But I thought they need to learn to get on the computer. So
Well, that's
if it was painful, but
data are data. So it's. But I agree. No, I think that's good. I think we need to.
We will keep them short so that it's not going to be like a huge burden to people too, right?
Right.
Yes.
Yeah.
I mean, maybe that would be part of the journal article that you would write, would be the instructors weighing in on the success beyond what the student assessments show.
And we also need a priori input, like is something. What would you want? As a community, what if we're going to standardize around, or at least start out with a couple of different packages? What would be most useful? And the thought was that we would, as a starting point, try to come up with one or two from each working group. So this could balloon. This could, ideally, we'd like to have more information than we would use in one manuscript. But yeah, we definitely need input on the individual success from instructors, both at the time that you're doing it, but also input in advance, so we know that we're doing something that's worthwhile for you.
And I think in the end, it's still going to be sort of like small sample sizes, because if you're in an oceanography department, you don't have interest in like teaching all the labs, or like if you're in a terrestrial domain, you like have less of a motivation to run ROMs, or like, so like there's going to be uniquenesses to each person who teaches with these tools, and not nobody's going to go through the whole sequence, I think. And I think we realize that, and we know that we will be working with sort of like a little bit of a diverse data set.
Right.
Yeah.
Just as an example, about 6 years ago, I did this, well, the TA for the course, who was a wonderful young lady, did this for a field course I was doing. We had 7 students in a 3-week field geology course, and we published an article on the curriculum and the assessment in the Journal of College Science Education. So talk about small sample size. I mean, that's pretty, even by geological standards, it's modest.
So 7 is not too small.
No, 7. That was 7 for one course only. So if we have, 3, 4, 5 students in a class at Delaware and Denham, we're actually starting to build up into a pretty sizable group.
Yeah, in a way, I think at the beginning, if you really want to get a more effective evaluation, it's probably good to have a smaller smaller amount of students. Because I cannot foresee we will get a really useful.
No,
For like 80 students.
I could not agree more with you. I've never seen a class, like we opened this up in at CU and like I advertise it in civil engineering, I advertise it in geology, geography, and like there's plenty of students that could like benefit from it. But then it boils down to like how many have other courses going on, and like so like the sample size is 10, like yeah. And I think that is the reality of like where this at the moment is. It may be a little bit different with those Excel labs. Those are more like they can be used in larger groups. We may advertise this a bit through the CSDMS lists or the CSDMS emails too, because sometimes it's the TAs that teach these labs, and it's not so much the faculty. But I think if you know you have a good TA and they're like interested in contributing, like that's as valid, and it doesn't all need to be, like the people who are in this room. And I actually do have a couple of volunteers who are not here now, but already said that they would do this too.
So we're going to broadcast this back. This call back through the different working groups and focus research groups as well. So you're going to be, pardon us in advance for
hitting you twice.
Duplicative emails. Anyway.
Yeah.
Does that cover it?
Yes.
Okay.
I think so.
So final point. All of the working group and focus research group directors or chairs, I've asked them to bring this up in the individual meetings. The idea of course of labs and assessment, and we can't. Irina and I can't be everywhere at all points in time. So if you guys would be willing in the meetings this afternoon to sort of bring that up as a discussion topic, I'd be very appreciative. Or at least if one of us shows up to help it continue after we leave.
Yeah. We're not. I think we have a little bit longer lunch basically, because I'm think that I covered what I wanted to cover, and only if people have pressing issues or like more questions. But like if you feel you heard enough, feel free to like sort of close it down, and we'll take it to individual level. Thank you.